welcome. Hope you guys are having a good time at Activate. And I'm going to assume you guys all went to Simon Hughes' talk and Andy Liu's talk, and you went to the keynote, and then I can skip over the first 30 slides. It'll be great. No, I'm kidding. I will zoom through things, but you've already heard a lot of this stuff before. I'm just going to kind of pull a bunch of this stuff together. This is on deep learning for unified personalized search and recommenders. And then I also tossed in some stuff that I thought is fun and different at the end on using these deep learning models to do kind of fuzzy tokenization. And I'll explain what that means as we go. I'm not going to really talk about this slide much at all because it's a waste of time. It's just about me. You're here to hear my talk, not look at stuff about me. You can look me up on LinkedIn if you want to know about what I've done in the past. What we're going to talk about is 3 different things. The first part is really just going to review the notion of personalized search and clickstream modeling for relevance improvement. And then we're going to jump into deep learning to rank. So nice way to squeeze together deep learning and learning to rank into one thing. Then once we've done that and we've kind of talked about how we've trained a deep learning model for deep learning to rank that has possibly personalized information as well as clickstream modeling in it, then we will use that model to do this thing that I'm calling deep tokenization. And we're going to use this to enable us to leverage the sparsity of an inverted index in much the same way that Simon Hughes talked about earlier today, except he told me last night that I'm doing it all wrong. So maybe it doesn't quite work as well as I think it does, but we'll see. He didn't say it was all wrong. He just said he's found some slightly better ways that I inserted at least one slide about because his talk came before mine. So search relevance for general, personalized search that also happens to have the regular kind of stuff you have. There's a whole bunch of different types of things you will do for search relevance, types of input features. There are, of course, the static document priors like page rank or overall popularity, sales rank, things like that. There's things that are kind of query specific, like query entities and query intent class labels that you can do where you've seen the query, but it's independent of the document. So it's document independent query features. Then, of course, there's the kind of usual stuff that we're used to in Lucene and Solr, which is the query document kind of overlap and similarity, which doesn't need to just be tokens. It can be any other sort of notion of query document textual similarity. Then there's features that come in as personalization that come in only when you tie in the user and either the query or the documents that are being seen in the result set. And what we call clickstream is what I would say was just kind of learning kind of the per query either click history or engagement history is what I'm talking about when I say clickstream. So that's kind of tracking the fact that over time, given query for iPad, it often leads to clicks on things that are, say, iPads, if you're in the e-commerce setting. I would put a Solr query that shows how you tack all this stuff all together, but it wouldn't fit on the slide because it's really huge. And this is what people do a lot of the time, and this is really good. It's actually a good way to hand tune. Fusion, Lucidworks Fusion sells stuff that lets you kind of build pipelines that put together all these things, a bunch of different pieces that all eventually create, at the end of the day, a big Solr query that kind of takes into account many of these factors and lets you weight them relative to each other. It gets pretty complicated, but it's pretty powerful. So that's everything you ever need to know about personalized search in the clickstream. Moving on. Haha, that's a slice of 20 slides I removed this morning. Deep learning to rank. Let's do this stuff in the deep learning way, because you guys have gone to hopefully some deep learning or some learning to rank talks, and so doing it without deep, you've already heard. So let's do it the deep way. In particular, let's encode features like text embeddings and other kinds of embeddings. Text encoding, which you may have heard of, not just kind of Word2Vec or Doc2Vec, but things like Elmo out of my former colleagues at the Allen Institute for Artificial Intelligence up in Seattle. Personalization, I abbreviate because I really needed less characters on that particular line. Just like I18N, I think it's actually P13N, not P18N, sorry. I got my wrong abbreviation. Then clickstream features fed into a deep learning model. And then we're going to talk a little bit about kind of how you would train these models and what you do at runtime. So we'll walk through these bit by bit. But first, why? You know, why are we doing deep learning? Do we really need to do this? The non-reasons that I have, or the reasons I don't have, is that it always gives the best ranking results. I'm not saying that deep learning is the way to do all possible rankings. It's always going to give the best results. It doesn't always. That's fine. Neither does logistic regression or not using learning to rank in the first place. Different things for different problems, different data sets. There's a no free lunch theorem hiding there somewhere. Also not a reason is because you can do super fast inference, you've got C++ and you've moved out of Java land and you're in like using, you know, you're in your GPU to do stuff. That's not my reason. That's not why I would like to do this. Or that the default model kind of like with no tuning and you just take whatever parameters you've got, just works kind of out of the box and is simple. Those are not the reasons why I like deep learning for this kind of stuff. My reasons, as not a data scientist, I'm more of a data engineer, is that as I've been learning this stuff, I found that as, you know, I didn't say, you know, modular or composable. I didn't say composable on this slide. Maybe it's in the next one. But Yashua Bengio, mentioned this as one of the big selling points he puts as a researcher, is that you've got these modular kind of subcomponents of deep learning models that you can pluck out and kind of pull together and compose into bigger models later. Or even freeze a model that's already been trained and then plug that into another model and it trains the other weights but leaves those weights alone. That kind of thing as a programmer is awesome. Like machine learning has always been like, you know, it's not, even if you know how it works under the hood, it's not, even if it's not a black box, you don't have an easy way of plucking out one of the trees in a random forest easily and then using that as a decision tree somewhere else and knowing that it's going to work well. You don't have easy ways of saying, oh, I'm going to just glue together this logistic regression with this random forest and I can plug them. Like you can make pipelines, but it's not easy and it's not straightforward. You've also got the ability to do, you know, what normally we would think of as fancy online training, but you don't need to just have online training. You've just got the ability to keep training. So you don't need to train it once and imagine it's static. My reasons for liking the GPU is not because it's super, super fast for, you know, for making things, you know, happen, you know, sub-second. It's because it means I get rid of distributed systems. Like I'm a distributed systems engineer, really. Like that's what I've been doing more than I've been doing machine learning for a long time. And the fact that I don't need to worry about shuffle things out to 100 machines and I can do it on the supercomputer that is called my NVIDIA little thing sitting inside my box is really nice. And I've found that you can train on much larger data sets now that you can do this. Then the really big reason is I like the trade-off that is not a free trade-off. That switch from going from domain knowledge and lots of feature engineering that takes ages and ages to very fairly naive vectorization and spending your time doing network architecture engineering is a trade-off that is not free. You don't just get everything for nothing, but instead of doing features as, you know, we're used to tuning search relevance by like designing features. But then at the end of the day, you're like, well, we should just be learning the weights. We shouldn't be hand tuning the weights. Well, not only that, you shouldn't be hand tuning the features. You should be learning the features, and that's what deep learning basically is doing for you. And this is exactly what I just said when that should have been on the screen while I was saying that. It should be noted that yes, you know, Updatable is not free. It is something you can do, but you know, if you're trying to update with different data than you started with, that's like a transfer learning. It works pretty well for many image kind of situations. Text is kind of an open problem to do it well. But yeah, the whole point that I really like about this is you're learning features. And when I get to tokenization at the end, I'll describe the way, as a text person, I'm trying to find ways of doing that in fun ways. Okay, so the kind of components that we're going to put into this deep learning to rank model. Let's start with talking about embeddings. So you all heard of Word2Vec or Glove or one of these other kinds of text embedding models. we kind of break up embeddings for text into kind of 3 different types. There's kind of the pre-trained ones that you just kind of download off of the web, and you get this 8 gigabyte file of things that Google trained on, 3 billion things from Google News. And they have good, nice, they've learned actually on that much data some really good models. Or you get, Elmo or one of these other ones as well. Or you can train it from scratch on your own data. This is what Fusion will do for you if you want to have word-to-vec model built as your vectorization technique for training your classification. You want to use this for feature engineering. If you've got enough data, that works pretty well. And then kind of the mix of the two is the fine-tuned model, where you take a pre-trained model on generic data, and then you fine-tune it toward your own particular objectives. So to be specific, the kinds of embeddings that I've seen work pretty well, that I like, the glove vectors are really good. You can get these slides later, or you can take a picture of it and kind of type out the thing, or use image recognition to pull it out later. But there's neural net language models that were trained on Google News as well, that you can get as a TensorFlow hub module. So you don't need to just download the big array of vectors and load that in with your own custom code. You can just have a TensorFlow model that you just kind of inject as one piece in your model, which is pretty nice. Fast text models are really good. Elmo is slower than I'd like, but they're super fancy because they also actually learn contextual vectors. So you learn based on an environment where you have text along the way, and the words will have vector meanings that can pull apart the kind of the fact that Java could mean coffee, or it could mean programming language based on the way that the sentence it's in gives you the context. Elmo will figure out a way to disambiguate those two. That's pretty nice. But it is much slower than I would like. Doing it from scratch, you have to kind of think about how many parameters you're actually learning when you do these kind of things. If you think about it, if it's a 300-dimensional vector, and you've got a vocabulary of tens of thousands or 100,000 words, do your multiplication there. Each one's got a float worth of data. It's millions to tens of millions of parameters. You're going to completely overfit if you don't have millions to tens of millions of examples. Once you've trained one of those, you can kind of consider it your own pre-trained embedding. You can reuse them in many different places if the domain is similar. Fine-tuning these models, taking the pre-trained ones, the word vector embeddings pre-train, I've found that this method requires a lot of care and feeding. It's really easy to just quickly, you have to kind of tune down your learning rate very low, and you have to have already kind of done this 3-step process where you bring in your frozen embedding, and you have the rest of your model that's coming after it, and you train the rest of the model having the embedding frozen until you get not fully converged, but you get kind of to a point where it's learned from your generic embeddings enough information to get a reasonable model. Then you kind of allow the embedding to now kind of learn from the model that you've learned in the later layers. And then you can kind of you basically customized your embedding model. Being able to do this, even though it's kind of finicky, I'm trying to think of other machine learning kinds of approaches that would let you do that. Just as an engineer, that feels like I have way more power. Embeddings in the Keras world, which is where I do my TensorFlow work. I don't do raw TensorFlow because that API is a just nightmare. It's really no fun at all. Keras, on the other hand, is actually very easy to use. You write, you want to get embedding, you can give your embedding matrix. If it happens to be, this is Python. I don't like Python, but that's what you have to do if you want to do deep learning, really. So I've got Python. It's really easy to just set up the model that has your inputs as your starting thing. This is a length length max len sequence of tokens came out of Lucene or whatever, and then it gets passed through as an input to your embedding layer, and now you've got what is a model that right now just spits out vectors, a sequence of vectors, if you give it a sequence of words. But then you can feed that into something else as another layer of deeper into your ranking model or your classification model or whatever it is. The nice thing is once you're done, the amount of work, the amount of code you have to write to get this model, that embedding out, if you've trained it. Let's say you gave it no embedding matrix, like I've gotten this code here. You've trained a model later. That means it randomly initializes it. Then it'll train your model. Your whole model includes a layer that is the embedding that's now trained. And now you can just pluck it out, and that's an embedding thing that's fully trained. Save that as a model by itself. Boom, you've got your own embedding. Trained to the particular tasks at whatever your objective function was. That level of modularity and composability is awesome. Okay, so embeddings, super useful as a component in a deep learning to rank style environment. But I should have talked about, in some ways, both before and after that, that's why it could have gone either direction, is text encoding. So that means that we've got text that comes in, and it's going to be a big string, right? That's what your input is in text. It goes through tokenization, and then it goes through various steps after that. But when I say I want to get encoding, that's kind of like you generate your TF-IDF vector from text. So it's got tokenization, then it does weighting. But in the deep learning world, that's also going to be encoding, where you're going to get a vector out from your whole text. But you don't maybe don't get to take a sequence of tokens. Maybe you have a sequence of characters. Then the question is what are you going to do to it? What kind of model, what kind of deep learning model are you going to pass it through? The two big ones for this kind of problem for text encoding are convolutional neural nets, one-dimensional convolutional neural nets. So an analog to a two-dimensional grid of text. Two-dimensional grid for an image is a one-dimensional grid of a sequence of tokens. The other way is long short-term memory networks. In particular, 1 to 3 layer bidirectional LSTMs are really super fancy, kind of state-of-the-art for most text encoding now. And I'll talk a little bit about why I'm not going to talk about those ones, other than that I don't really understand them that well, in a second. So first off, let's think about text encoding. Characters versus words. Word embeddings. If you're going to train them from scratch, it requires, as I said before, millions of parameters, thus maybe many gigabytes of training data. It's kind of semi-unsupervised in the sense that you're just training on the text. So you can usually find many gigabytes of training data for your domain. Not too bad. But it also needs good tokenization and pre-processing. That's going to be the same in your data science pipeline, Python, as at your query time, Java, C, something else. This is a really easy way to mess things up. This is like the kind of, in the old world of Lucene and Solr, of like, you got the wrong analyzer at query time that you had at index time, and you've got it off for TORI. This is like, you mess up somewhere in here, use NLTK in your data science pipeline, you forget what there was in the stemming or the regularization rules, and at query time, mismatch here can be kind of devastating. Sharing that code is hard. So maybe instead try just character sequences. Does that make any sense? Can you do that? It turns out that this actually sometimes works for old ML. Like our classification models at Twitter, for example, it was text classification, about 200 categories for classifying tweets and the web documents that they linked to. And we would classify them. It had to work on every language in the world. We didn't have any identification of what the languages were. And we actually just said, we found a bunch of different things. We eventually trained on good old logistic regression. Inputs were overlapping byte foregrams. Consider each byte foregram as a 32-bit int. And you just hash those into a space and use those as your features. You don't need to tokenize. You don't even know if the text is tokenizable. It could be a random semi-language done on Latin character sets, but they're trying to text each other in Arabic, so they used Latin character sets upside down, which we discovered in our data set you'd see that sometimes. So using character sequences is not unheard of, even in the old days. Nice thing is it works on smaller data because there's much less parameters. You don't have a big embedding matrix with millions and millions of parameters now. You have lots of parameters, but not millions and millions. And the really nice thing is you don't need to worry about tokenization anymore. You're not doing tokenization. Your model's doing tokenization, I guess is the big punchline that I'll get to later. And this is also, just to mention, this is not my clever trick. This is, doing this kind of thing has been around in old ML for ages. In fact, my team at Twitter was doing this stuff on regular classification before this deep learning version of this kind of stuff in 2015. So let's say we're going to do text. I guess this is I should have put that radioactive symbol earlier of saying like this kind of like data science pipeline versus query time is, more dangerous than you think. Okay, so characters versus words. I'm going to go often with characters for most of the rest of this talk, but let's talk a little bit about comparing and contrasting one-dimensional convolutional neural networks with long short-term memory networks. What do I have to say here? In some sense, this is really just kind of giving you a picture about what is a 1D CNN. A 1D CNN is really taking a sliding window of some number of characters or words over your text, and each one you're just kind of dot producting that into a bunch of vectors that start random, and you're going to learn good vectors that are going to be projecting into a different space, and then kind of concatenating out the outputs of those dot products into another vector that now is still sequential because you're doing the sliding window, and as you slide the window across, you're getting different dot products out, and you're basically doing random projections to start. The random will become less random later because you're trying to learn features. You're extracting out features from your text, which maybe is features at the level of character n-grams. If they're words, they're going to be word n-grams. But you're getting out features, and then eventually you're doing this step again and again and again, and the next layer you're taking sliding windows of those original sliding windows, and occasionally you're pooling them together, and now you're looking at larger and larger windows of your text. At the end of the day, eventually you're going to have some classification, regression, ranking problem that is going to be the objective function that says whether you learned good features or not. And when you learn bad features, you're going to propagate those errors backwards through the network and learn to get a better projection. Reason why I'm sticking with CNNs for the rest of this talk, for the most part, is that I understand that. That seems to make sense to me. That's random projections that you learn to get less random. You're finding features. Their features are at the level of little windows of text. If it's characters, it's windows of character n-grams, and then cascadingly bigger windows of text as you go further down. LSTMs are keeping track of the information at a more, you're keeping track of the state as you're scanning this window across. It does the same sort of thing where you're scanning windows across your text, but you're keeping track of what you've seen before. That whole notion of how you remember that and what you forget and when you lose it is still a mystery to me. So I'm not going to talk about that too much more. It is actually better. It tends to get better results for text understanding. It's also a lot slower and is not very parallelizable on GPU. So other advantages for why I don't need to learn it yet. I do. But yeah, to kind of give you a slide saying what I just said right here is that the other kind of reasons why I like CNNs is that it does have much fewer parameters, so it can train on smaller data sets and it's going to train faster. And yes, it's GPU friendly, that's great. It's dissectable in the way that LSTMs aren't. LSTMs learn all this stuff kind of all at once. For each layer, all you've got is the output state for the whole text you put in, or possibly just the whole, and you've also got the output state for each individual window you slid over, either the word or the token. But it kind of does it all in really one or two layers, whereas CNNs tend to be much deeper, which means you've got different features learned at each layer, and you can start pulling those out and using them for different things. And I feel like I've got more room, more levers to twist and pull, which is also the bad side too, because you have many more hyperparameters, many more things to tune, many more things to go wrong. And in fact, maybe at the end of the day, it's going to take just as long to train because you're going to run over a big search across all the hyperparameter space. So even though you can do this really fast on less parameters with GPU, you've got to search over a much, much larger space than LSTMs do. So there are pros and cons. I'm going to stick with the guys that I like for now, at least for this talk. Typically requires more code. That's true. CNNs do require more code to write because you're configuring a much bigger thing. But it's still not a ton. You know, you don't need to read everything on here, but really this is like a, you know, a full CNN in Keras for text, an encoder. So this is not doing, this is generating, you know, a vector per document as output. It doesn't yet have what is the objective function really you're going to do at the end of the day. I've got it listed with binary cross entropy as loss there, but really it's going to get wrapped into another, the optimizer you're going to have and the loss you're going to have is going to really get decided by when you actually put it into the model that you're going to use, like your ranking model. But really, the amount of code here is more than an LSTM. An LSTM, you could fit in half the space. But it's not like a ton. I've written much more code just to do, you know, good logistic regression, really. We don't need to understand all that. Once you've made one of these encoders, you know, the nice thing, you know, in terms of what it looks like. So I got 13 minutes left. Wow. I'm going to zoom through that. Not important. But number of parameters, 300,000 or so, even at like 7 layers deep. Not too huge. Gradually sequence. This is the length of your input sequence, say 64. By the time you get down to the end, you've pooled over bigger and bigger ranges. So now you've got it down into like only 4 different chunks at the very end because you've kind of broadened out bit by bit as you've gone. Quick show of hands, stuff to do with personalization or deep tokenization. Okay, good. Oh, wait, then we got a bunch after the fact? Okay, we'll do both real quick. We'll do it in an artistic style. So this is collaborative filtering on canvas with acrylics. This is an old piece that I now have to include in every talk I do from now on. It's actually, I wrote this a long time ago and I've used it in many talks even if it's not necessary. Point being, collaborative filtering actually can act as a pre-trained embedding for using features to do personalization with deep learning. So just as you've got word vectors that come from Glove or Word2Vec or whatever other thing, at the end of the day, when you use it as an embedding model in Keras or PyTorch or whatever, it doesn't know where those vectors came from. It doesn't know that they are skipgrams or continuous bag of words or whatever. It uses them as inputs and then learns from that later in the rest of the model. You do the same thing with the user features or item features of a alternating least squares matrix decomposition. Feed that into Keras. It'll just take it as personalization input. Kind of cool. It actually does work. I haven't seen it do fine-tuning well yet, but fine-tuning is already tricky by itself. Clickstream is actually the same sort of thing. We can actually just take the doc ID embeddings from personalization or the kind of query. So you look at query document correlations and maybe counts. Well, I won't say correlations. That's too big a word. Query document counts of clicks that you got. Make a doc ID embedding for each of those clicks. And you can kind of do it the same way as you did for user IDs. If you try to do this from scratch in the model and you don't kind of inject it externally, it can overfit pretty easily, I've found. In some ways, it's not the worst thing in the world, because what it basically does is learn the popular documents for each click, and it overfits to saying, whenever I see this query, I'm just going to return this document, which is sort of what the simplest possible clickstream boosting will do anyways. Many of our customers at Lucidworks find that they like the signals boosting that they turn on to the point where they just sort by those signals boosts. And just throw away the text ranking for the head queries entirely, which is what this model ends up doing as well. So it's also learning the intuition that it sees that, oh, I like your clicks already. The head is so big and the tail is so long that I'm just going to just return these in this order. So sometimes deep learning models can just heavily overfit. It's usually bad. Sometimes it's actually pretty okay. This is one of the cases where I think sometimes it's okay. That is not important. This is a model that has doc IDs as inputs. I've just hashed it 4 times into, like, say, 1,000 dimensions. So you don't have it in millions of dimensions anymore. And I've hashed user IDs similarly down into 1,000 dimensions. So you're not generating a really big embedding model. And 96 dimensional doc ID as if you had a factorization, a matrix factorization at dimension 96. And for user IDs of dimension 128, they don't need to be the same anymore because they're not actually the factorization of a single matrix. And you just concatenate them in with your query encoder. That was a CNN that we already described the code of. And you concatenate it with the doc text, say the title, or the snippet. You wouldn't do this for really long documents. It'd be too big. And you pass through a couple more layers, and you train a ranker. Total number of parameters, still only 600,000. On character CNNs, this is still way smaller than just word2vec by itself. So you can run this on not huge data. 3 million clicks, say, is what I've tried this on. I'm going to skip over objective functions you do for doing this kind of thing. I just showed you doing it for ranking as an output, like the scoring layer at the bottom. You can also train for other kinds of things like text classification or text generation, or the identity function, which is kind of regenerating your text from the input. I'm going to skip over that stuff. I'm not going to talk about distributed processing because you don't need to do it anymore. Do it local for the most part. You can naively parallelize with Spark or whatever to have trained hyperparameters in parallel, but for the most part, a lot of the stuff can be done really quickly locally. I'm going to skip over query time inference by just saying AMLeap is actually pretty cool. It supports TensorFlow as well as scikit-learn as well as SparkML. There's a link on this slide. XGBoost as well. It's pretty cool. When I saw them saying they were going to basically re-implement the kind of inference layer for each of these things, I'm like, that's never going to work. I'm never going to see it. It's never going to be done. And then they went and did it. It was like a year ago. I looked at their stuff and I'm like, oh yeah, that's not the right way to do it. They got to find some way to have an abstraction layer that actually properly gets the a way to deserialize a Spark model and then turn that into something else. You got to do it generically. You can't write this stuff all over again. If you see their actual code, they've written inference layers for every single one of these models. Except some of it is not super hard. Some of it, when it's like, say, TensorFlow, TensorFlow Java already exists, and they sort of wrap it for you. So my voice is actually holding up, which was remarkable because last night I was giving this talk to Simon Hughes and Jimmy Lin, and this is me hand-waving my way through this talk. Apparently this picture was taken last night, and I didn't shout for so long that my voice is completely gone, so we can finally move on to something completely different. This is me trying to explain to them my notion of deep tokens for Lucene, and hand-waving my way through it, and they're both great audience listeners because they both showed either why I'm wrong or why it's trivial, or both. But we'll see. I don't think it is. I think there's still some possibilities here. So at a high level, we're going to do a couple things. We're going to say we've built this character CNN internals for the text encoding, and we've trained like a ranker, for example. So we've got a ranking function that it's trying to learn. Remember what these things are trying to do is they're trying to find features that are going to optimize your objective function. So if your objective function is query ranking, they're trying to find features that are best at getting the query encoding vector and the document encoding vector to be in a place where they're not necessarily cosine similar to each other because you actually feed it through a fully connected layer at the end. So it can actually learn an inner product that is maybe not linear. So it's not really an inner product. But it's learning a way to get a similarity metric, and it's learning the right features. So you do the char CNN on each of your encoding layers, encoding submodels, and then we're going to do locality sensitive hashing on the intermediate layers of each of these CNNs and pluck out binary codes from them. So we're turning our text into sequences of binary codes, and then we're going to index them in Lucene that leverages the sparsity of the index. Sounds great, but why should this even work?
Can you go back?
Yeah.
A little bit too abstract for me. So the deep tokens.
Yes.
Does this replace, for example, stemming?
Yeah. It replaces even white space tokenization. It replaces stop word removal. It replaces tokenization. You take text as input, big block, and then you scan this thing over it, and it's spitting out a whole bunch of abstract tokens at multiple layers of abstraction. Some are going to get different things. We're going to see it a little bit in deeper. We got 5 minutes, but we're going to see what I mean here. So maybe we'll skip over like what the CNN is emitting. Note, CNNs aren't sparse at each layer, but they're kind of sparse actually, because you're often using rectified linear units, which mean you've got lots of zeros, because whenever the input was negative, it flattens it out to 0. So it's not really sparse though, but it's kind of half sparse. But it's all positive. So you got to be careful the way you hash these things, because they're actually, they're all in the same quadrant. They're all positive. I'm not going to talk really about the internals of CNN for right now, but the idea is you're sliding over windows, you're projecting down to numbers, you're getting out feature maps at each layer. At each layer, you're getting k-dimensional vectors. And so you're not getting k-dimensional vectors for the whole text, you're getting sequences of them. Over each window it's looking at, you're getting a different vector that you've emitted that is partly sparse. They're going to be basically the same length, input and output, if you've done pre and post padding of your sequences. Don't worry about the details, but it basically means that your sequences look the same length for a while until you start doing pooling, and then that means you're kind of growing your window out bit by bit. Getting this information out of these models is actually really easy. Coding-wise, in terms of in Keras, is like a couple lines of code. 2, that's all they are right there. You're going to grab out layer 3 and layer 5, the outputs, and then you've got a new model whose outputs are no longer the objective function you had. They're now the intermediate layers 3 and 5. So they're going to generate sequences of vectors. So the kinds of things I've found when I've tried to do this, there are problems, but the good things are that at the earlier layers, you learn simple features like some kinds of morphology in English. I was running over like Best Buy query sets in the sense that it was a Kaggle competition from 2011 or so. So people are searching for iPad 2. It was probably before iPad 3 was even out, really early on. So there's this kind of weird kinds of morphology I was finding in here. But you find things like spacing and word endings. You start to get, as you get down to the layer 1, I did it in blocks of 2 CNNs at a time, so layer 1 is really layer 3. You're getting like word roots out as simple features that are often found, and articles. And here's where you start finding the actual things that are removed in later layers. So when you find pronouns and articles, you start getting them here, and they get often projected out. Found that they weren't always projected out, so stop word removal is not a thing that's just completely solved by this approach. But it shows promise that it could remove it because it's finding them, and now it's just a question of making sure you can turn on those neurons to kind of to remove them later on. And then you start seeing words that are projecting to the same thing via misspellings because you're seeing subword units. So you're not seeing whole words anymore. You're seeing the first 3 characters and the last 3 characters, and they're mapping to a single neuron of the next layer. You're also seeing things like it's noting hyphenations and concatenations of words where you get kind of camel-cased words as well. And each time you get some pooling at layer n, you're starting to find bigger and bigger windows that you're looking at. How deep can these go? Turns out that some people have done effectively like a VGG, if you've heard of in the computer vision world, one of the VGG networks for image classification has gazillions of many layers. This is a 29-layer CNN for text on characters, and it's even trained on pretty long sequences of text, up to 1,000 characters long, which is a lot of text to give to a CNN. People usually think of like LSTMs, the only things that can actually handle reasonably long text, but you're actually getting pretty good inputs for text classification, not full understanding, not reconstruction. So maybe it doesn't work for all kinds of cases, like say search ranking, but at least in their paper, they do this on pretty long inputs and many, many layers. And it still only has, well, actually, at this number of layers, it has a lot of parameters. So I've already said that what we're going to do with these vectors outputs, vectors don't fit in Lucene still. I've got like 35 seconds. Oh, man. Here's a picture. We hash them. Locality sense of hashing often works pretty well to generate codes. The way you generate a code is you make a random vector, and you say if it falls on the left side, it's a 1, falls on the right side, it's a 0. That's bit number 1. And you keep doing that with a bunch of different vectors, and this divides up your area into very, very simple clustering. Depending on how you do this, you can either get really good similarity or just near duplicate detection. It works. I know. See, it's hearing it from the back, hearing it from the front, hearing it all over the place. So I can't even make that stop. Stop, please. That's very sad. OK, well, let's just say that I have seen some experiments where you can actually see some pretty interesting things that map to the same character engrams that map to the same hash codes in ways that you wouldn't have expected and you wouldn't get from normal tokenization. So I don't know if this stuff is perfect, but for example, you see queries that people are doing searches for Lord of the Rings extended. And we actually found that a 4-character input RIMF actually fed to the same thing that you got from space RIN and E space RI, because they all kind of occurred in Lord of the Rings. But ring didn't hash to the same thing, because ring was an ending to many words that end in something or ring. And so you actually end up finding that you can actually capture some of that similarity that you wouldn't have, you can catch, there are other versions of spell checking and so forth, but the kinds of things you can find kind of very multi-word, quote unquote word, S space Z space 8 getting hashed as a 5-character engram to the same place as Lumix, which was sort of weird. That was pretty deep in, that was at least 4 layers in. Still to do like a full measurement of what happens, like there's a precision versus recall trade-off here, obviously. The thing is, you've got tunable ways of doing it. You've got like maybe 8 different layers you extracted out tokens of different types to use. And you can tune whether you're searching on layer 3 or layer 5 or layer 8. And what, when you do indexing, you could say, I'm going to remove anything that occurs, any bucket that occurs in more than 10% of the entire corpus. We're going to remove it entirely. That requires global analysis, so you don't get to do that per document very easily. But you can analyze on a sample and then try to see how that works. Yeah, there are still many challenges. Stop words don't always get removed. Getting optimal hash functions is hard. And if you do optimal hash functions, you can do it dependent on your data. But then if you change your data, your hash function changes and you have to reindex. And on big data, it's a big pain in the ass. So maybe don't do that. Lots of other things. I'm going to have to just say at this point, there are a few more slides. There are people that have done this kind of thing before. The THC network this week is very appropriate. This is a CNN for text hashing, and apparently they didn't think that it would be all weird to call this text hashing on CNN's THC. Interesting. But yeah, here's a TLDR slide while you say, yeah, hashing, exactly. But I'll say, thank you very much. Hooray.